Let us now turn to the Reionization era, which is currently one of the frontiers of observational cosmology, and theoretical one as well. A brief history of the universe is as follows. There is a recombination when the universe was about 380,000 years old and microwave background was released. At that point, there were no more sources of light in the universe. But the dark matter fluctuations keep collapsing, and eventually gas that would fall into those potential wells would get sufficiently dense to make stars, igniting star formation in first protogalactic segments. Their UV radiation would then start reionizing neutral hydrogen in the universe around them. And eventually those bubbles of ionized gas would start to overlap, at which point the universe becomes transparent again to the UV radiation. It is, of course, always transparent to the radio waves and infrared, but at wavelengths shorter than Lyman alpha line of neutral hydrogen, it was completely opaque. That is what we call the reionization era, and at that point you can say that galaxy evolution proper begins. The universe was reionized by the first stars. Inflow into massive black holes, or any black holes, probably also played a role, but we think that most of it was done by the first generations of stars. It turns out that those first stars that formed just from hydrogen and helium, without dust as we see in Milky Way today, or heavier elements like carbon or carbon monoxide molecules and so on, were different. In the process of star formation, the protostar has to collapse. That means it has to lose energy or cool, just as we're talking about collapse of galaxies requiring extra cooling. And in star formation around us, molecular lines play substantial role in doing that. But for the first stars, only molecular hydrogen was available, so they couldn't cool quite as efficiently. And that leads to formation of very massive generation of first stars. Multiple theoretical studies have indicated the same thing, that the very first stars probably had masses of the order of hundreds or thousands of solar masses, much more so than stars that are formed today. Because the very massive stars are also very hot and very luminous, they provided excellent sources of UV radiation to reionize the universe. And indeed, if you look at theoretical Hertzsprung-Russell diagram, HR diagram, the plot of luminosity versus temperature, and if you compare where those stars without heavier elements, just hydrogen and helium are, they kind of parallel the main sequence of young stars today, except they're much hotter. And the reason they're hotter is that they were slightly smaller, and also there were no metals to absorb UV radiation in their spectra, which means they're even more efficient as sources of ionizing radiation from the first galaxies. As those first stars evolved, they would explode as population 3 supernovae. You may remember that population 1 was stars of the solar disk, population 2 were the old stars of galactic halo and bulge, and by the extension, population 3 were the very first generation of stars made out of hydrogen and helium alone. Well, they do cook up some heavier elements and disperse them in supernova explosions. That creates some small abundance from which the population 2 stars are formed. People have looked very hard to discover stars with no metals, but there aren't any left. The oldest stars, the most metal-poor stars, are maybe 100,000 of the solar abundance, but they still have something, and so that's what we think the first population 2 stars are from. One interesting thing is that many of these massive stars probably exploded and created black holes, and in that process also created gamma ray bursts. What's shown here is the mass of the remaining remnant neutron star or black hole versus the initial mass. And for a large range of masses, black holes formed and a gamma ray burst ensues, except for a small interval in mass where star is completely disrupted and there is no remnant. So we can expect to see gamma ray bursts from the very first generation of supermassive stars in the reionization era. Indeed, here was the very high redshift gamma ray burst discovered in 2005. And just as we can look for quasars or galaxies using the drop technique, here we can also see there is a strong drop in continuum right at Lyman alpha line. And that is characteristic of the high redshift objects. And real spectrum was obtained, as shown here, and that confirms the photometric determination. Interestingly enough, in this particular object, the host galaxy of it shows some metals. So this was not from a really young galaxy. This galaxy already evolved some. And here is one at redshift 8.2. The redshift measurement is not 100% certain because the spectrum was very poor, but photometric data indicate that was indeed the correct redshift. And this is probably the most distant object to which somewhat reliable redshift estimate was made. What's shown here is the histogram of gamma ray burst redshifts that pretty much parallels the history of star formation in the universe. And this one is obviously out there beyond redshifts where other galaxies have been seen. We think that these first stars started forming maybe around redshifts 20 or 30, the first protogalactic fragments. They probably reionized the universe by about redshift 10 or 15, and that's indicated by microwave background measurements, as we'll see in the next module. But then, conceivably, there was a lull in that primordial star formation. And after the first supernovae from population 3 stars exploded, then they started making young population 2 stars. And they may have reionized the universe in a second wave of primordial star formation. And by about redshift of 6, the whole thing was pretty much finished. So one possible scenario is that after the recombination in the dark ages, when there are no stars, no sources of light, you have the very first generation of supermassive stars reionizing the universe, creating the metals, creating now population 2 stars. The low mass population 2 stars are still with us. They're in galactic halo and globular clusters, but the very massive ones have, of course, exploded early on. And then they can do the second wave of reionization, which may not be really distinct. We can model this process using hydro simulations that include dark matter, gas, as well as radiation and supernova explosions. And here are snapshots from one of those. And you can see that the ionization fronts propagate through the primordial intergalactic medium, the original cosmic web, in a way that's not simple and spherical because some hydrogen shields the material behind it. But eventually, it all does get ionized. In the next module, we will talk about this in a little more detail.